And I'd like to invite our first speaker, Anya Seward, who's going to be talking about the role of geoheat in New Zealand's low carbon energy future. Thank you.
Thanks, Janet.
Oh, and by the way, we did have 4 people in the session. We now have 3, and we have an hour. And so each person feel free to go a little bit over time, not way over time, but you can talk for up to 15 minutes probably if you like.
Now the question is, can I use this if I don't touch it? Is that all right? Those online? Is that all right? Okay, good. Because I just know with one of those I'll smack it or whatever. So kia ora, my name is Anya. I work for GNS Science. I'm based up at Wairaki. We have 4 offices around the country, 1 here in Dunedin, 2 in Wellington, and 1 up at Wairaki. I'm part of our geothermal team there. So I'm just going to caveat this presentation by saying I'm a subsurface person. I am a geophysicist. I study the physics of the Earth. I use physics to understand the Earth. So my connection to what goes into the grid is really just what I know what's happening under the ground. So all the grid connections and the answer to this question is actually going to be on you guys. So I am just putting this up there and telling you what I know and what I think it could be, but it's up to you guys to make it a reality, I hope. So the theme of today's symposium is changing relationship with energy. These are going to be our take-home messages. Heat is energy. And secondly, there's no more efficient way to heat than if you've already got heat. So sounds silly, but it's not. So I'll just start by going over why heat is important and why heat needs to be considered alongside your other energy sources, your electricity and your gas. And then I'll go into a bit more about geoheat. So heat makes up 1/3 of New Zealand's overall energy use. And that breaks down, according to MB, 84% of industrial processes use, sorry, I should say, yeah, 84% of industrial processes use heat. And of that, 56% is generated from fossil fuels. And that equates to 8 million tons of CO2 put into our atmosphere every week, every year. Every week, that would be scary. Our process heat industry consists a lot of production, paper production, dairy processing, timber drying, refrigeration, and some of these fit under commercial use, some of them fit under industrial processes in our categories, depending on who you speak to, but they all use heat. Up there is your spectrum of heat for all your industrial and commercial processes. In our homes, Hannah pointed out earlier, we have 32% of our electricity is used directly for heating. 30% of our hot water, approximately, is heated, and 10% of our electricity bill goes towards cooling, and that number is predicted to increase. That's a lot of electricity that is converted into heat. Now to go with my first point, transition to a low carbon energy future, we cannot overlook the importance of decarbonising heat. So what is geothermal heat, or geoheat? It's geothermal heat. And I've just got a little video so you don't have to listen to me that explains it.
Geothermal heat is a renewable, low-emission energy source. Humans have used geothermal heat for thousands of years, and when this energy is used directly, we call it geoheat. It refers to all forms of heat present within the Earth, from the intense heat deep within the Earth's core to the warmth absorbed from the sun at the surface, as well as the high temperatures produced by volcanic activity. Aotearoa, New Zealand's unique geology, offers abundant and accessible geoheat, closer to the surface than in many parts of the world. From the Southern Alps to Northland, our land produces geoheat at varying temperatures.
What is on that map for you? This map here is the results of some work that my colleague has been doing over the last few years, and that's looking at how heat is transferred throughout our country. So it's looking at our thermal rock properties, our tectonic setting, our erosion rates, the physical properties of our rocks, and what that means for how heat is stored and transferred in our subsurface. Caveat, it's got a color scale on it, so it does look like the Alpine Fault holds as much heat energy as Taupo Volcanic Zone. That is just a color scale thing. But that having said, we do have a lot of hot springs along the fault. The other thing to point out here, blue doesn't necessarily mean there's no heat, it just means there's less of it.
Geothermal heat is a
Don't need to listen to that
renewable...
again. I'll put that in there in case it didn't stop. So heat stored in the ground is generally stable throughout the year. As the video said, we've been using heat in New Zealand for a long time, generally around the high temperature stuff. But before we even settled here, in Europe, cavemen lived underground. They knew the ground was warm in the winter and cold in the summer. So this next slide sort of gives you an indication of how we access the heat. In high temperature areas where there's a lot of energy in the subsurface, we utilize it for geothermal electricity generation. You wouldn't be able to do that with the heat provided down here. However, there is still heat in your ground that could be extracted for residential heating, office block space heating, greenhousing, and there's more and more technologies coming on that could help, more and more technologies being developed that can convert low-grade heat into electricity. So this figure here just sort of shows different ways, what we call direct heat, that's where you directly extract the heat that's beneath the ground, and indirect heat, where you utilize something like a ground source heat pump or a bit of technology that will convert your heat into electricity. There's a big conversion error, even with a conversion loss. Even when you're in the high temperature systems, when you're producing electricity from geothermal steam, you're losing about 85% of your heat, and your energy is just being dissipated or re-injected into the ground. So you've only got a 15% efficiency when you convert to electricity. And then when that gets to your house, you convert it back to heat. So how do you efficiently use it? This video sort of just indicates, we'll take you through a little bit about ground loops, and they get designed, this is how they work. Cold flow goes from the house, pumped through your subsurface, picks up the heat, comes back into your building, converted through a heat pump for space heating, and out into your house for heating, for space heating. In a factory, generally you need high temperatures for more energy to run your industrial processes. And this last slide here, just sort of indicating that you don't actually just need the ground. Your lakes and water bodies also have stable subsurface temperatures and can be extracted for heat conversion as well. So when I say heat conversion, I'm not converting from heat to electricity. It's going from heat to heat, and what you need is the delta T. I guess the main benefit that I didn't mention here is that for space heating of your houses, you still need electricity to run your heat pump. But the conversion and the coefficiency of performance of your heat pumps these days are up to about four CPUs. So for every 1 unit of electricity put in, you get 4 to 5 times more energy out using your subsurface temperatures. That way. So I've just got a couple of slides here to say this is not new. As I mentioned before, people have been using subsurface heat for ages. In New Zealand, these are within our type of volcanic zones. These are the high temperature users. We've got wood drying facilities in around Taupo. In the middle there, we've got Hora glass house that's using steam that they have to cool to do space heating in their soils and their glass houses. Obviously, swimming pools. Got one down in South Island, Hamner Springs, so outside the TVZ. That bottom photo down the bottom there is Meraka, which is a milk drying facility where they're taking the steam from the Mokai power station. The heat from there, waste heat to dry their milk powders, and the waste heat from there goes down to those glass houses in the back there. That's 5 acres of glass house. So they use that waste heat again to warm your glass house, and then the whole circular economy. Then the waste of the rotting fruit and stuff that they don't sell goes into a worm farm, and that soil gets regenerated and goes back in. And so it's a nice little ecosystem they've got there. And the one with the long pools there is the Taupo Prawn Park. Have you ever been up Taupo Way, where they grow tropical prawns up in central New Zealand, North Island? Outside the TVZ, I just thought this was good to put in here. These are, I guess, examples where they're using ambient ground temperatures or lake temperatures here. The picture in the middle there is a Lower Hutt Council building. It needed earthquake strengthening. So when rebuilding, they put the pylons down and lined them with some piping, which they use to extract heat from the subsurface aquifer to heat and cool their building. Same in Christchurch after those earthquakes down there, a lot of ground source heat pumps were put in to extract the stable heat from the subsurface aquifer systems they've got there for heating and cooling of their commercial buildings. Up in the corner there, I know it's not outside the TVZ, but it's the Wairaki Golf Course just outside Taupo. They've got a water feature there that they've got a heat exchanger in, and they use that water temperature to heat and cool their club rooms. Very nice. This map on the side here was our attempt to try and classify who's using heat directly in New Zealand and what it is. So it's very hard to capture, particularly on a residential scale. Taking a bit of a jump here, sorry. This is an example of work. I guess the point of this slide is to say that people are getting really interested in the opportunities around ground source heat pumps and using heat directly. This table here is produced for ECA as part of their RETA, the Regional Energy Transition Accelerator Program. And the example there is looking at a glass house. So this is looking at a glass house that's based up in, it's a typical glass house, it's 5 acres producing tomatoes. And they did a quick analysis to show what cost savings you could have when you comparing ground source heat pumps using that stable ground temperature that's just in your ambient ground to, say, an air source heating system. I'll just highlight those two numbers there. They basically, I haven't got the electricity numbers in here. Gone for the money because people relate to money and how much savings you get, which directly relates to efficient heating, efficient energy use. So compared to an air source heat pump, if you put a ground source heat pump in to do your heating and cooling, based on your ambient ground conditions, say 15 degrees, I think here we're a bit colder, so it might be about 10 to 12 degrees, your ambient ground temperatures here. But over a space of a year, you're saving 200,000 to 350,000 in energy costs and operational costs. If you happen to have a glass house somewhere where you've got warmer subsurface temperatures, say Tauranga, that number increases a lot. So this is for a glass house. They generally pump 60-degree water round for their space heating and their soil. The other reason for putting this slide up and why we've got all those logos there is we've just partnered with Vegetables New Zealand and got a primary industry sustainable futures and fibres futures SFFF funding to have a look closer at the geothermal resources around to help convert our glass houses who are predominantly LEG heated or coal heated. And so we've got a little project working with them over the next 2 years. So this is what my future looks like and what I want to put out to you guys. It's district energy schemes. It sort of builds up on what Hannah was talking about earlier in our residential sector. If we're converting the way we're heating our housing, we look at electricity. She did some nice graphs about how much you save from that. We put ground source heat pump in on a district system. The installation costs drop dramatically. Your efficiency for your house increases dramatically. Your energy poverty and your energy equality should levelize with support of funding. So this is my utopia. That's what I want you guys to figure out. Can we do this here? They do it in Europe. That's really all I can say is they use ground temperatures there that are around the same 15 to 20 degrees for heat exchanging, heating an office building who needs heat during the day, dumps their cold into the ground, and they swap it around, and that causes an ice skating rink or some other buildings on the same loop. So, take-home message: heat is energy. There's no more efficient way to heat than with heat. Geoheat is everywhere. Geoheat is low emission, and Geoheat is available to you.
Great, thank you, Anya. We've got about 5 minutes for questions if anybody would like to ask one.
Watch the video again.
Going back to the district heating slide, what's the smallest residential district that would be economic to do in New Zealand? Do you know? Like, is it 50, 100 houses that it might be economic, or?
So we have a colleague who'd be able to answer this probably a lot more eloquently than I will. It all depends on your building usage, your building's demand, and the geology you're in. We have ground source heat pump systems already installed in New Zealand on a residential, or there's one up in the Alps somewhere. That's a lodge, a cabin, and their payback for their upfront investment to savings, I guess, was 7 years. So when you're looking at the grand scheme of a single house, New Zealanders own their house on average 7 years, but I guess with more we invest into our houses these days for double glazing and insulation and all of that stuff, for those of us who are retrofitting everything, we stay in them longer. So if you build on more houses, the scale of what's the word? Scale of economics, the payback is really decreased, right? And if you're going for these new builds or in districts that are going in, you're already putting roads in, you're already putting your subsurface electricity, you're already putting the subsurface gas lines. Not much more to put a subsurface water pipe. Yeah, there's a big push in the US to run these out to communities. It's being run and operated through the gas utilities. They see that gases are limited or a restricted non-growth area, I guess, non-uptake. So they're trying to work both markets at the moment, and it's really working well in some areas on the eastern coast where they don't have the high temperatures. So I'm not an economic person, I'm not a power person, but that's what I glean from conversations. Yeah.
That's 50, about 400 houses.
Yeah.
And you're going 400 houses going into Lake Howea,
Yeah.
special housing area for affordable homes. 400 homes heated this way.
You're speaking my language here. We tried this up in Taupo with a subdivision. We came in a bit too late to get them thinking about their subsurface things. The biggest concern we've had talking to developers around district heating schemes is who owns it. So we need someone to own it and run it because people don't seem to want to take that up and think it's different somehow. And that's sort of been the feedback we've had so far, but the rest of the world's doing it, so it can't be impossible.
Right. Well, thank you. That's super interesting. Lots of food for thought and clearly a huge potential if you get the right people on board and the right settings, I guess.
That's why I'm here instead of at Geothermal Week, or Geothermal Workshop, which is in Auckland right now. But
Yeah,
you know,
it's really important to get these
yeah.
messages out.
This needs to be heard by people when they're thinking about how they're decarbonising our future.
Yeah. Okay, well, let's thank Anya
you.
very much.